Hello, I am Derek Owen from Team 10, and this is our final demo for CSCI 490 Deep Learning, our final project. Our project was the Segment Anything Model, SAM, on the Cityscapes dataset. So here's our data loader, which is just finding the RGB images stored here in left image 8-bit. From the Cityscapes dataset, and our annotations from the Cityscapes dataset stored in here, and we are using the label IDs.png files, which are integer IDs per pixel. We only use the train and test splits, or no, not the test. We use the train and val splits, as the test split annotations are not made publicly available by Cityscapes. So that was our dataset loader, and then we have our utilities file here, zero-shot utils boxprompts.py. And here we generate the box prompts, which we use to prompt SAM. Here's how we generate the box prompts, and we use these box prompts in our zero-shot approach. And then down here we just have some intersection over union IOU helper functions. And we can move on to our actual evaluation of the zero-shot approach. And for this we are just using the pre-trained checkpoints from the SAM GitHub, and it's saved here. And we go box by box, box prompt by box prompt, using the SAM predictor, which we loaded up here, and we clone the actual Segment Anything repository here, and we're just importing from that right here. So we go box by box, and using the SAM predictor we get our candidate masks, which we take the highest confidence level mask from that. Yeah, right here. So predictor.predict, and we get we take the max score, the highest confidence level that SAM outputted, and finally we compute the per class intersection over union and the mean intersection over union. And over here we have our results from that. So we got a mean intersection over union of 0.7192 from our zero-shot approach. And here is where we tried to improve on that. We used a small semantic head on top of SAM's image encoder. So first we have our SAM Cityscapes head class, which we kept the model intentionally simple. We used two 3x3 convolution layers with batch normalization and ReLU activation, then a final 1x1 convolution that maps features to class logits. And then we build the frozen SAM predictor, or the image encoder. It doesn't it only uses the image encoder, not the prompt encoder or mask decoder, because we are just using it as a frozen feature extractor. And here's where we do some pre-processing to get the images in a format that SAM expects. Then down here we have our actual training loop. Here's where we actually get the image encoder, which we use as frozen feature extractor from the segment anything repository. And then we do the training using cross entropy loss on the 2,975 training images from cityscapes. And in our results here, we got, this is the output from that training. So we did 5 epochs with a batch size of 2, using all of the train and validation samples. And we got a mean intersection over union of 0.8013, which is a bit of an improvement over the zero-shot approach. And here we have a little demo script, which basically does everything we have talked about so far, but for just a single image. And it's using the pre-trained weights for the semantic head and that we have here in our models folder. Yeah, so this was trained on my desktop computer with my 3080, and I just downloaded it and I'm using it for inference. So let me actually run demo.py. So we use Conda as a virtual environment, and then Python, and it's just going to ask for an index 0 to 499 of the 500 validation cityscapes images. So we'll give it something. And now it will run. Okay, so after about 5 minutes, the demo is done, and it should be saved right here. Here's 89. So here's the original image, and here's the original segmentation with our 5 classes highlighted. And here are the box prompts we generated from that. And we plug those box prompts into the segment anything model for our zero-shot approach, and this is what it gives us. And here is, if you give the image straight to segment anything model, it gives us this as the image encoder, which we use as the frozen feature extractor for our model, and here's the result from our model.